I'm a faculty here in the physics department. It's a real pleasure to introduce Professor Girish Agarwal, who's a visiting Infosys chair professor. Girish is a university distinguished professor at Texas A&M University. He specializes in quantum optics and is the author of Quantum Optics, published by the Cambridge University Press. His work is widely followed with an H index of 97 with more than 36,000 citations. He's been recognized by a large number of awards, including the Max Born Prize from the Optical Society of America 98, Towns Medal of OSA 2022, the Physics Prize of World Academy of Sciences 1994, the Humboldt Research Award of Germany 1997. Further, he was elected Fellow of Royal Society UK in 2008 and is a Fellow of many other academies and societies. So Girish gave a very nice talk in the department about 2 weeks ago, and hopefully he'll have some new stuff that we can all learn together. And this is a Quantox talk. So this is organized by the Office of Quantum Technologies here at ISC, which has been organizing these talks for the past 1.5 years. So we are glad that you can again join us for these for this hybrid talk here. So please.
Yeah. Thanks everyone for coming. Thanks Akshay for this rather long introduction. I thought it would be brief. So, as Akshay said that 2 weeks ago, I had given it already a talk on quantum sensing, quantum imaging. But Jaideep Basu wanted to give me another talk related to quantum metrology. So what I have done for the talk today, there would be some new topics and there would be some overlap with what I presented in the colloquium. Okay, so let me start by reminding you what's everyday knowledge, how the classical sensors work. If you have some kind of medium and you are trying to probe the properties of the medium, you put a laser beam typically on the medium. You look at the transmission, or you can also look at the scattering. And by looking at the characteristics of transmission or the scattering, you infer the properties of the medium. And some of the important properties would be like density of particles, absorption wavelengths, oscillator strengths, relaxation parameters. So these are all the parameters that you can infer from measurements like this. And when you want to sense something accurately, then the small perturbations on the medium are of special interest. And this therefore raises the question that how small phase changes introduced by the medium and the absorption of the medium can be detected. If the phase changes are large or if the absorption is large, then we don't care how well we sense. That question arises only if these perturbing parameters are small. So next I want to show that these measurements are what's called the short noise limited. What is short noise? So we have a coherent field and the output also typically is coherent field. But we all know that the coherent fields have photon number fluctuations and therefore the output also will have the photon number fluctuations. And since you are measuring the signal, essentially it's the measurement of the photon numbers at the output. Therefore, the output will carry the signatures of the photon number fluctuations which are contained in the input laser field. And these photon number fluctuations are typically Poissonian. Therefore, the signal would have Poissonian fluctuations. And that means that the measurement would have a noise which will go as square root of the signal. And this ratio, signal to noise, would go as a square root of the signal, and that is called the short noise limit. So the kind of measurement that I described on the previous slide will have signal to noise ratio given by this, and we want to develop strategies where we will have signal to noise ratio smaller than this value. And that's where the ideas from the quantum metrology come in. And what we would like to do is to replace the coherent light by quantum light. Now, since we are talking of the estimation of the parameters, the parameter estimation theory is very well developed, and this is developed in terms of what's called the Fisher information and this Cramer Rao bound for unbiased estimation. So if X is a parameter which you want to estimate from your measured data, then you define a Fisher information via this relation. So this quantity Pjx is the probability of getting an experimental result J. So it means you get the experimental result for X as some value J. And then you define this way using these measured probabilities. And once you have this quantity, then one says that the estimate of the parameter, the sensitivity of estimate, as this as the lower bound, which is in terms of the square root of the Fisher information. If you have continuous measurements, then you replace this discrete sum by an integral over the continuous measurements. Please note that this Fisher information involves mean value of a logarithmic derivative. See, this quantity dp over dx divided by p would be the logarithmic derivative. And so the Fisher information is in terms of the logarithmic derivative of the measured distribution. And we can now use this to move on to what's called the quantum Fisher information. So now we are trying to estimate parameters for quantum systems. So we move away from classical estimate theory to the quantum systems. Okay, so the parameter estimation, so we prepared our probe in some initial state. It's a quantum mechanical probe prepared in an initial state. The probe interacts with the medium. It evolves to a final state. Then we carry out a measurement. And from the measurement, we will have the estimator. So we can prepare the probe in a suitable initial state, and we also decide about the measurement strategy, and from the measurement we estimate this parameter. So for quantum systems, there are important questions that what is the best initial state of the probe and what is the best measurement procedure. And these questions can be answered based on the extensive developments in the field of quantum optics. Okay, so first I need to define the quantum Fisher information. And I had already mentioned the structure of the Fisher information for the classical systems. Guided by that, I define the Fisher information for the quantum system as this is the density matrix of the system. X is the parameter that you want to estimate. And in terms of this, L is the logarithmic derivative, and you have L square here. So this is the most general expression for the quantum Fisher information. And this quantity L is defined by this. Now, in general, it's rather difficult to compute this L the way this is defined. Keep in mind that rho is the density matrix of the system after the probe has interacted with the system, and X is the parameter. So it's the differentiation of the density matrix with respect to this parameter. Okay, so depending on whether the system is open or system is undergoing unitary evolution, we can obtain the form of this logarithmic derivative. All right. So now we look at the case of first an open system, and for the study of absorption, so if the system has an absorption, then the system is an open system, and we have again input field, outgoing field, and we can compute the fluctuations in the output field, the signal, and we can define what is called an error sensitivity. So this is the sensitivity of absorption measurement in terms of the fluctuations in the output divided by this derivative of this. And note here that this quantity involves fluctuations in the input field, and therefore this would be minimum if these fluctuations are 0. In other words, the input field is a photon number field, the Fock state of the radiation field. Okay, so this estimate is based on this object, and let's say what the quantum Fisher information teaches us about it. So we have to look at the time evolution of the system. There's an absorption here, and system can also be at some temperature T. The dynamical evolution of the field is described by this complicated looking equation, which is the equation for this open system. And from the solution of this dynamical equation, you can calculate the output density matrix. And from that, you can calculate the logarithmic derivative and the Fisher information, and that gives you the same result. So you calculate the quantum Fisher information, and from quantum Fisher information, get the parameter estimate using Cramer Rao bound. So which means that this measurement of the fluctuations in the output photon number and estimating delta alpha in this way, it would be the best measurement for absorption. Now for systems undergoing unitary evolution, one finds much simpler results. For such systems, the Fisher information, this is the quantum Fisher information, can be estimated from the quantum mechanical uncertainty in this variable G, and the variable G is defined in terms of the unitary evolution of the system. U is the unitary evolution of the system. And so if you know the unitary evolution of the system, you can compute this quantity G. Once you have the quantity G, find out the quantum mechanical uncertainty in the input probe. So 0 refers to the input probe. Further, if the unitary evolution has this simpler form, like this, X is the parameter that you are estimating, theta is the corresponding operator. In that case, G becomes just this operator theta, which is called the generator of unitary evolution. And in such case, the sensitivity of the parameter estimate, so this would be the Cramer Rao bound, would be given in terms of the uncertainty in the variable theta in the input state. And therefore, if you want to have the minimum or the maximum sensitivity, you would like to have this uncertainty to be large. And this would also remind you of the Heisenberg uncertainty relation. But there is a difference here. So delta X is the uncertainty in the parameter estimate. It is not the uncertainty in X. It's the uncertainty in the estimate. But this quantity is the uncertainty if X is the displacement in the momentum in the input probe, which is used to estimate the parameter. Okay.
Can I?
Yeah, go ahead.
So this essentially is the concept of the squeezing of states. Is that correct? That is, you need to create a lower uncertainty in one of the parameters to get a higher uncertainty in one parameter.
That's right. That's right. But the difference is that, as I just explained, that this is not exactly the Heisenberg uncertainty relation, because this quantity delta X, which is coming from Cramer Rao bound, that is the uncertainty in your estimate of the parameter X. Okay. So it's not the uncertainty of X in the input state, it is the uncertainty in the parameter estimate. So that is the key difference. I mean, very often people just, when they look at it, they think, oh yeah, it's just the Heisenberg uncertainty relation. Yeah, so then, I mean, this, as you said, that we would like to have an input state here which has large momentum fluctuations. Okay, so I'll now describe to you an application of the previous, what I said on the previous slide. And that's the, so this is an experiment on the quantum amplification of the mechanical oscillator motion. So you're trying to look at the oscillator displacement and how best we can measure it. And So the result that they have found here in this experiment that they report, that they improve the measurement sensitivity by a factor of 7.3. Okay, so how that's achieved? So of course this this paper, it describes, it says that here is an experiment, here is a procedure which achieves this, but they don't use any of the framework of the quantum metrology theory. And I was in touch with Dave Vineland, and he said, well, he knows nothing about quantum physical information. He has to have a course 101 in quantum metrology. Anyway, so we look at this from the perspective of quantum metrology. So the idea here is the following, that the experiment is done with the ion trap, and you are looking at the motion of the ion, the center of mass motion of the ion. So you start ion initialized in the ground state. And now, since we want to measure the displacement from the previous slide, we need to have an input probe which has as large momentum fluctuation as possible. And that can be achieved by applying this operation on the ground state of the ion. And so what it does, it changes the ground state of ion to this. And so as you can see from this picture, that this state has large fluctuations in this direction, which corresponds to momentum direction. And now you want to measure the small displacement of the ion. So this is the displacement operation. And so a small displacement means you shift this ellipse slightly in this direction. And in the experiment, then they applied this anti-squeezing operation. And this then results the displacement which is amplified by the parameter corresponding to this operation. So this is stretching e to the power r will correspond to this stretching. And so the small displacement that you want to measure is now amplified by this factor. Okay, so how do they detect it? So you're talking of the ions, and you will have to convert the displacement of the ion to the electronic degrees of freedom, and then you measure the population in the electronic state. And that's how you infer quantum characteristics of the ionic motion. So here are the details. So you have the ion, you have the two hyperfine electronic states. So one state is here, and let's say another state is here. And the ionic states corresponding to this electronic state is a bunch of these states. And for this electronic state, you have a bunch of states. So you have the whole harmonic oscillator spectrum here, whole harmonic oscillator spectrum here. Here the electronic state is different from here. And so what is done to read out the ionic motion, one applies Raman pulses. So see, you make a Raman transition. You can start from here, come here. You apply a pulse here of certain frequency, a pulse here of another frequency. You tune these frequencies so that this energy separation corresponds to this difference. And that's how you play around by transferring the populations from different levels to different levels. I mean, here you can do, for example, a population transfer between two ionic states. So you can make a Raman transition between two states in this ladder. Or you can make a Raman transition from one state of this ladder and one state of this ladder. And these Raman transitions can be effectively modeled like a Jaynes-Cummings interaction, which is very well known in quantum optics, and which would look like this. So A corresponds to the phonons or the ionic degrees of freedom, and these raising and lowering operators will correspond to the transition from this electronic state to this electronic state. And once you implement this, then you can read out the ionic motion in terms of the populations of these states. And these populations are further read because these are the populations in the ground levels by bringing another field which transfers to one of these far away excited states, and you look at the fluorescence. So that's a standard method of reading out the population of any electronic state.
There are not, unlike diamond vacancies, there are multiple states.
Yeah, so you tune the frequency. The frequency tuning is very important. And with precise tuning, you create a precise Raman transition between two levels. Okay, so what they do? So they can read out the population of each of these levels, and let's say you read out the population of this level, and you introduce also another field here at some angle phi. So you would do a pi/2 rotation, and this thing contains this angle. So then you find out the population of, say, one of these electronic states as a function of this phi, and you will have these interference fringes, and from the interference fringes you get the visibility or the contrast, and from this form you figure out what is the signal to noise ratio. So they estimate the sensitivity of measurement based on the signal to the noise ratio. And the signal to the noise ratio in the limit when this amplification parameter, this was e to the power r, times the small displacement is small. So keep in mind that alpha I is very, very small displacement that you want to measure. G itself could be like 8 to 10, but the product is much smaller than 1. So in this case, the signal to the noise ratio under this limit simplifies to this. And so you see, they can read out the small displacement just from this signal to the noise ratio. Okay. So what would be the quantum physical information view of this experiment, quantum metrology view? So we have an initial probe now. This part becomes the probe, quantum probe. This is our system undergoing whatever development you have. In this case, it's just the displacement. And then this part would be the readout, the measurement scheme. Okay, this is the measurement process which includes this operation. So we can compute the quantum physical information for this setup, and the quantum physical information for this setup turns out to be this number. So this is just the amplification factor. So this would be e to the power 2r, and therefore this will be the sensitivity according to the Cramer Rao bound, which will go as 1 over this amplification factor G. And this estimate based on the quantum physical information will coincide with the estimate that you get from the signal to the noise ratio under these conditions. So, whereas if you look at the official information for the measured data, so this is how you would define the official information for the measured data. So this is the from the interference fringes, maximum, minimum of the interference fringes. And the official information for the measured data, depending on the G value, would be given by this, depending on the alpha value. So if G alpha is much smaller, then this measured physical information coincides with the quantum physical information. Whereas if alpha becomes little larger, then you find that this is the measured physical information, whereas the black line would be the quantum physical information. Now we know from the quantum metrology framework that the Cramer Rao bound gives us what is the best that you can achieve. It does not tell you what experiment you must design to achieve that. And so clearly in the experiment, they achieve the best for alpha values times G to be much smaller than 1. That is this. But if you want to measure little larger displacement, it's still small, then you don't do as well as the quantum physical information would predict. However, if you can measure the full phonon number distribution, then the quantum physical information and the measured physical information using the phonon number distribution, they coincide. And therefore, this would tell us that an alternate measurement strategy based on the measurement of the phonon number distribution would be best. Now, people have measured the phonon number distributions for the ion traps, but they are not easy to do. Okay, so there are various other examples that you can discuss in the interferometry. So this is the case of atomic interferometer, and so this is the atomic interferometer part, which is a unitary operation. All interferometers correspond to unitary operations, and this would be the initial quantum preparation of the probe, and this part would be the measurement part. So this one, which some of us had discussed in the past, is very similar to the strategy that Vineland's group adopted for this experiment on the ion traps. And this is the initial preparation, and this is the measurement part. Okay, so for the open systems, I had already mentioned, and there's also a lot of interest, a lot of papers are being written on quantum thermometry. So again, the estimate of the temperature of a system, how well you can estimate the temperature of the system. If you look at the dynamical evolution, it has two parameters here. One parameter is the gamma, which corresponds to the absorption in the medium, and another parameter is the temperature of the medium. So N of T is the temperature, and in the steady state, so no matter what initial state you have here, in the steady state, the system will go to thermal equilibrium at this temperature and T. And you can make an estimate of the temperature or the correspondingly this parameter N of T. So sensitivity in the measurement of the temperature, this would be the result for the finite time. Eta would be like e to the power minus 2 gamma T. So here are some more details on the quantum thermometry aspects. So estimates at some time T versus the estimate in the steady state. So this is the parameter eta, and this indicates the number of photons in the incoming probe. So you can have 0 photons or 1 photon in the incoming probe for different values of this parameter. So this parameter basically corresponds to the length of the medium, because this T would be L over C, so that's related to the length of the medium. So there are regions where you do better. This ratio. So depending on the measurement occurs for large T or a small eta. So we also devised another strategy where you divide your measured time interval into number of smaller intervals, and you can do a whole sequential set of measurements, and that give you higher sensitivity of measurement. Okay, so now I can tell you a little bit about some of the experiments that we have been doing, and before that I'd like to tell you something about the two-mode squeezed states, so which are generated by this unitary operation on the vacuum. This is the structure of the generated field wave function, and one can have variety of two modes. There could be two polarization modes, or there could be modes with frequencies close by. And the important feature of this state is that the photon number difference has highly quantum features. If you look at this structure, both the modes have the same number of photons. And therefore, the photon number difference and the fluctuations in the photon number difference, they all vanish. So this is just a experimental illustration of the fluctuations. So if we have two coherent beams, look at the noise on each, very noisy. You add these two intensities or subtract these two intensities, still you have a lot of noise here. For the two-mode squeezed state, if you look at each beam, that's very noisy. Whereas if you now add and take the difference, so you find that this is the difference, the red ones, and the blue ones are for the addition. And so in quantum metrology, one makes use of these reduced fluctuation, reduced quantum fluctuations in the difference of the intensities of the two modes. And you can calculate this quantity. So this is the two-mode squeezed light, intensity difference fluctuations. Compare it with that for a coherent state and plot this on the dB scale in terms of this R parameter, which was in this unitary evolution. And so this is the quantum characteristic of the two-mode squeezed light. So that's called intensity difference squeezing. And we can use it in a variety of measurements. And I describe these measurements in much greater detail in my colloquium, but I'll just say briefly about these measurements. So the way we generate two-mode squeezed light is by the process of four-way mixing in atomic rubidium vapor. And this is the process of four-way mixing. You have two photons generating one conjugate photon and another probe photon. And these probe and conjugate photons each form two-mode intensity difference squeezing. And this is the actual data, the measured data, the amount of squeezing. So this is the short noise limit, and this is for the two-beam squeezed light intensity difference squeezing of about 6.5 dB. And so we use it for the absorption measurement. And so we say that what is the sensitivity of the absorption measurement using this two-mode squeezed light versus the standard quantum noise limit. And this is the what's called quantum advantage, shown as a function of the absorption parameter. And this region is really very good. It gives you about 1.25 dB of quantum advantage over the laser sources. And because there are a lot of unwanted absorption optical losses, so if you calibrate for all those things, this will translate to 3 dB of quantum advantage. Let me skip that.
Girish, I have a question.
Yeah.
So in this two-mode squeeze state with two photons, how close are the wavelengths of these two photons? And does it matter in your experience?
In my system, because I'm making use of the intensity differences. So it does not matter. Okay. But there would be other situations where you would like to use the amplitude. There it matters. Okay, so for those kind of problems, you would like to have two modes having more or less the same frequency.
The degree of entanglement will also change.
Yeah, but I'm saying that, I'm not directly using the standard way the entanglement is defined. I'm using the fact that the intensity difference has this important quantum characteristic. To solve based on the idea of intensity difference. All right. So now finally, I'd like to describe to you some other theoretical ideas. And these are, we were guided by what we learned in quantum metrology. So what we learned in the quantum metrology, that the use of the quantum states of light or the quantum states of matter can give you much better estimate of the parameters. And that's what the whole quantum metrology is about, that how much better you can do. So we came up with a new idea, and the new idea is this, that we can use these kind of parametric interactions. And I'll have to go back. I should have written it down. So these kind of interactions. This is a unitary transformation, and you see this is like an effective Hamiltonian, which is sitting in the exponent. You put an I and another I there, so that would be an effective Hamiltonian. And if you have an interactions of these kind, whether the two mode or single mode would be A dagger square and A square here. So these are generally called as the parametric interactions between the two modes A and B. So, yeah. So what I like to show to you, that how these parametric interactions can lead to enhancement of the interactions. So let's think of a cavity QED setup, very generic type of cavity QED setup. You have here a qubit, which could be any kind of qubit, which is coupled to a cavity. And we know that what is the strength of this qubit when it's coupled to the cavity. And what we would like to do, we would like to enhance the strength of the interaction. And it's possible to do so by thinking that the standard cavity is replaced by a cavity which has a parametric material. In other words, in the cavity, I have a nonlinear or a chi2 material, and the chi2 material adds to this kind of interaction.
You need a nonlinear material medium there.
Yes, of course. Yeah. So if we look at the Hamiltonian of this system, and the last term is the standard interaction of the cavity field with the qubit, and these are the free terms. So when you think of a qubit interacting with a cavity, you have this term and this last term. And now I am adding this extra interaction term, And what I want to show that the addition of this term, it amplifies effectively the strength of this interaction. So, this is back to the idea that the quantum amplification of interactions now. And there are certain conditions that you must maintain in order to have the stable operation of this system. So these kind of conditions are needed. Okay, so you can play around with some unitary transformations and so on, and then transform this Hamiltonian into a new Hamiltonian of this form. So there are two terms here. There are terms here which are going as e to the power r, and there are terms here which are going as e to the power minus r. So this immediately suggests that, let's say, if r is in the range 1 to 2, then this part of the interaction can be dropped, and you are left with just this. Then effectively, you have enhanced your coupling strength by this factor. So that is the key idea, that that in any standard cavity QED setup, you can enhance the strength of this coupling by bringing in a Chi2 material. All right. So we use this idea further to look at effective interaction in the cavity between two systems. We have been doing a lot of work with the magnetic systems, and that's why you see here a picture with the ternium garnet spheres there. But the idea is fairly general. It's applicable to any two qubits or any two collective systems. And so now if you think of two systems here in a cavity, and you drive one of these systems. So by driving this system, this one is excited. And then these two are non-interacting with each other. But the excitation from here is transferred to this one. And why this happens? Because this interacts with the cavity. So the excitation from here creates photons in the cavity. These photons interact with this system and they excite this system. Therefore, we have here a cavity-mediated interaction between these two systems. Okay, so the question is that this cavity-mediated interaction, can I enhance by using this idea of introducing parametric interaction? Now, there are a large number of experiments with many different kind of systems where these processes have been studied extensively. That is the transfer of excitation to the other one via the cavity. This is a standard system that has been studied in the past in many different contexts. And now we'll show that by the addition of this parametric interactions, we can enhance these cavity-mediated interactions. Okay, so let's forget about the mathematical details of the system. One thing which we always need to worry about these systems, because we have lots of parameters, and so we have to decide that what is the stable region of operation of the system. the reason that these kind of interactions are called parametric devices because they give you parametric gain at the classical level. And when the parametric gain becomes too much, then the system becomes unstable. So that's why we need to check all the time that that we are working with the appropriate parameter regime so that the system behavior is stable. Okay, so the parameters important parameters would be interaction of these with the cavity and the frequency detuning factors and this new parameter capital G. So what this slide shows is this enhancement factor in the cavity-mediated interactions. When you introduce this additional parametric interaction compared to the case when there are no parametric interactions. And so that gives the enhancement factor as a function of this additional parameter G. And this is the stable region, that part, white part is the unstable region. And so this is a line plot of the enhancement factor. Depending on the detunings you choose and the G values, so you already start getting factors like 10. And of course, here the enhancement factors could be fairly large if you start approaching the region of instability. But you are still away in the stable region. And why all this happens? Because you need to examine the relevant eigenvalues in the underlying dynamics in the cavity system, and you discover that there is an eigenvalue goes to 0. So that means in this parametrically coupled cavity QED system, you have a mode which is very long-lived. And this long-lived mode gives you this large enhancement factor. You can also understand this in many different ways. If you don't have the parametric device there, then these are kind of pathways. So cavity has no photons. System 1 you excite, you put a photon in system 1, no photon in the system 2. Now this from the system is transferred to the cavity, and then from the cavity it can be transferred back to this or back to this. So this state can go to this state. So basically what will happen is kind of, if it were a closed system, you would have a periodic transfer between these two states. It's almost like a block oscillation between those two systems. Okay, but of course we have the dissipation, cavity decay, and the decay in the systems. So that would be the case when G is 0. When G is non-zero, then many new pathways open up. You see, when you transfer this photon to the cavity, now cavity can have 2 more photons from this parametric interaction, it goes to this, and then many new states start getting generated. And that's what leads to the enhancement. So this would be the quantum amplification of the interactions in cavity QED. And just like cavity QED is such a universal subject, so this idea would apply to all types of the cavity QED systems. Okay, so what I have told you, I have given you a general framework for quantum metrology, and examination of best possible quantum states, optimum measurement strategies, and giving you a little bit about quantum advantage in absorption spectroscopy, applications based on squeezed states of matter like ionic motion, interferometric applications of multi-particle GHG states. And we have many other papers on related subjects. So I've given some of the references here. Quantum light enhanced enabled spectroscopy, several publications. This one, the latest one is on the was called coherent anti-Stokes Raman spectroscopy, application of entangled light to coherent Raman spectroscopy. Coherent anti-Stokes Raman spectroscopy, quantum imaging applications, quantum microscopy, and so on. Thanks very much.
Questions for this?
In your Higgs sphere problem, what are the typical dimensions of the Higgs sphere that you anticipate using?
Well, typically, those spheres are like, let me just try to remember a number. Could be like 100 millimeter.
Then it's a collective excitation of magnons.
That's right.
It's not really individual magnons, although we write them with creation annihilation operators.
Yeah, so it's a collective system.
We have collective excitation. So
Right.
does this same idea of parametric amplification of quantum states apply out there when you have collective system?
Yeah, of course, yeah, same thing would apply. So, in those systems, there are experiments on what's called spin current there, people have called. And there are two PRLs on this transfer of excitation from one Higgs sphere to the other Higgs sphere.
But that would be classical. You can just have dipole interactions.
That's
That's
right.
so large, right?
That's right. So you have that. And then on top of it, if you introduce this kind of parametric interaction, then you can get these very large spin currents there.
And then you don't have a loss parameter in your equation.
Now, loss is there everywhere.
Yeah.
No, Hamiltonian, I don't have the loss, but
Okay, I omega there, but that's not.
no, this one is the driving field,
Right.
this field. But loss parameters, these are all to be introduced at the level of density matrix. That's the correct description for the loss parameter. So we have introduced all these loss parameters. These have gone in the calculations. So here you have term here which have these loss parameters.
I have a more naive question regarding the quantum thermometry part.
Yeah,
So if I understand, the thermometry comes because you can determine the phonon occupation through the experiment. And for different
Yeah.
temperatures, that's going to be different.
no, that's one case, and the other case, when the light is propagating, even if there are no phonons there, the propagation of light through a medium depends on the temperature of the medium. So that affects the photon number distribution. Yeah.
So coming to the, fine, I get these two separate points. So, but if I look at the phonon number distribution part,
Yeah.
the phonon number distribution of the atomic system that you're using, right? That is the magnesium. I think that's what.
So it depends on the system.
Correct.
Like ion trap case, I would look at the phonon number distribution of the ion.
Correct. So is it possible to use this system to determine the temperature of an external body in some way?
Well, you see, temperature, when I say system is at some temperature, because it's interacting with an external body, that's how it has acquired the temperature. It's like putting a thermometer in my mouth, right? Thermometer is my measuring instrument, but it measures my temperature.
Sure.
Yeah. So same way that as external body, which is influencing this medium, and its influence on the medium, I look at the medium. And once I gain this knowledge about the medium, from that I infer something about the external body. So this quantum thermometry, I mean, currently most work on quantum thermometry has been of theoretical nature. There are no experiments.
Experiment. Yeah, so that's
So far.
interesting to see the.
Yeah.
Any questions? Any more questions? From the students, maybe? Any questions?
All the students.
Even the simplest question is welcome.
Current PhD students and undergraduate.
I have
I can
Abdullah.
answer a simple question. The amplification or whatever enhancement of the signal to noise ratio can come from combining multiple signals.
Yeah.
Which is what you described. You may have two modes or something
Yeah.
like that. You combine them, but you can also enhance it by a long-term exposure, combining the results at different times, and probably with a Fourier transform and things like that. This is in some sense what the astronomers use simultaneously. They use the superposition for in space, which they use with large-scale baseline interferometry, but they also use long-term exposure, and then use the Fourier transform of the signal to again improve the signal to noise ratio. So can there be an analog of something to do that time?
Yeah, but those are all classical techniques.
Yeah, they're probably-
So those classical techniques cannot beat the short noise limit.
that is true.
Yeah. So what they will say, okay, I have certain this kind of measurement, it gives me so much signal to noise ratio. Okay. So that S over N, I mean, the way by using all these techniques is bigger than S over N measured by some other people. But that is still bounded by the short noise limit.
Yeah, but the point of this combining multiple inputs is that the short noise is independent on the inputs,
Yeah.
and the signal is correlated.
Right.
And that is where you.
So I mean, I have no answer to this, that maybe on top of what we are doing with these quantum states, if we add some of those classical kind of ideas, whether that can improve things further. That's an open question. But if you have completely classical system, I mean, you do much better, but still you would be bounded by that.
Questions? If not, let's thank you.
Thank you.